Good day, doctor. Today our group want to present about the iris dataset pattern recognition, present by the section 1, group 8 and section 2, group 1. Next slide. Okay, these are our group members. First, my name is Thomas Selvan, son of Pamnadi. My metric number is BI220143.
My name is Harini Anandaran. My metric number is DI220138.
My name is General Dr. Sanmugarcha, and my matrix number is DI220174.
My name is Abdulkareem Osman. My matric BI22042.
And myself, Katyayani Selvaraj, and my matric number is DI220145.
Hello, my name is Tamirasi, and my metric number is DI220136.
Okay, the presentation outline is introduction, application domain, methodology, and demonstration about the SAS, result and discussion, and conclusion. For the introduction, this project explores the plant species classification using the iris dataset from Kaggle. It focuses on identifying 3 iris flower types, Setosa, versicolor, and virginissa, based on 4 features: sepal length and sepal width, petal length and petal width. The data is clean and processed to ensure quality, then used to train machine learning models. By applying algorithms such as decision tree, grading boosting, and random forest, and logistic regression, the project aims to find the most accurate model. The highlights the role of machine learning in recognition pattern, supporting scientific research and automatic classification in biology. The application domain. Species classification is important in biology, agriculture, and ecology to identify plants based on physical traits. Manual classification is time-consuming and may vary by individual. Machine learning offer a faster and consistent solution. Supervised learning models like decision tree, random forest, and logistic regression are commonly used for classification tasks. The iris dataset Setosa versicolor virginissa is used as case study in features, sepal, and petal measurement. The data processing include imputation, normalizing, and encoding and splitting for model training and testing. The decision tree module achieved the highest accuracy with easy interpretability. Machine learning improved plant classification by supporting research tool, agriculture system, and mobile apps. It enabled fast, scalable, and data-driven pattern recognition for various scientific applications. Next slide.
Okay, thank you, Thomas Sullivan. I shall continue with presenting the model and the algorithm used to develop the project. So as we know, multiple machine learning algorithms were implemented using SAS Model Studio, including, as the first is the decision tree, where it is employed for its interpretability as it splits the data set based on the feature values to form logical and rule-based predictions. And the second model algorithm used was random forest. Random forest is an ensemble learning method which was used to improve classification performance by aggregating prediction from multiple decision tree trained on random subset of data like iris dataset. And the third is gradient boosting, where this is included for its strength in modeling complex relationship by sequentially training weak learners that correct the errors of previous iteration. And the fourth algorithm used is logistic regression, where it is widely used on the statistical method for classification, was also applied to provide a baseline model that reveals flower measurements to specific probability. Next slide. I shall continue with the methodology also. So the machine learning life cycle picture is included in the methodology, which is define project objective, data preparation, model building, model evaluation and interpretation, and model deployment. So for this iris dataset, the objective is to build a classification model that can identify the specific and the species of an iris flower based on the 4 numerical features, which is the sepal length, sepal width, petal length, and petal width. Next slide. So on the data preparation, it involves organizing, cleaning, and transforming the data set to ensure it is suitable for machine learning algorithm. So although the iris dataset is clean and well labeled, it still requires the pre-processing step, which are the data properties at the first place, where the data properties of the iris dataset consists of 150 observations and 5 attributes, which is the 4 numerical features, which are sepal length, sepal width, petal length, and petal width, and one categorical target variable, which is the species. For the data pre-processing, followed by an explicit imputation node, which ensures the compatibility with automated workflow by maintaining uniform data completeness. Next, a transformation node is applied to the scale of these 4 numeric features, standardizing their ranges and minimizing the risk of biased model performance caused by different measurements unit. And lastly, the third process in the data preparation is the data data partition, which is used to assess model performance effectively. The iris dataset is divided into 3 subsets using stratified sampling, typically executed via pro-partition and or pro-service select. So stratified sampling ensures that all these 3 iris species are proportionally represented in each subset, preserving class balance and minimizing bias during model evaluation. So these selected methods stratify ensure balanced distribution of species across the training, which is 70%, validation 15%, and test 15%. So the figures are included for the data set partitioning, which shows training set consumes 70%, testing set consumes 50%, and validation consumes 15%. That's all from me. I shall pass to the next team member.
Thank you, Kak Yayani. So I shall continue with the data preparation, which is the second step of the machine learning lifecycle. So here, for experimental setting, the input variables which comprising sepal and petal dimensions are designated as predictors, while species is set as the target variable for classification. And then the experimental process is carefully tracked to allow performance comparison across multiple algorithms just now mentioned by Katyayani. So as you can see here, the figure shows the square error after option, which is done by the decision tree. So here, the figure displays the model performance matrix for a decision tree applied for the iris dataset. The result indicate a high classification accuracy of 0.9583 and a low average square error of 0.0324, demonstrating that the model predicts species with high precision and minimal error. And then we shall continue with the square error change to class target, which is also by the decision tree. So here the figure displays the model performance metrics for a decision tree applied to the iris dataset. The result indicate a high classification accuracy of 0.9583 and a low average square error of 0.0324, demonstrating the model predicts species with high precision and also minimal error. And then here shows the result after setting, which is used by the gradient boosting algorithm. So as you can see here, the figure presents a model performance results after configuring and executing a gradient boosting algorithm on the iris dataset. This ensemble technique, which combines multiple weak learners to form a strong predictive model, yields an average square error of 0.1777, noticeably higher than that of the earlier decision tree model that shown in the figure before. And then carry on with the result after setting for the forest algorithm. So here the figure displays the performance metrics of a forest model, which is the random forest evaluated on the test dataset. The model achieves a high accuracy of 0.8750 and a low average square error of 0.0367, indicating reliable classification with minimal prediction error. These results suggest that the forest model offers a strong balance between precision and generalization, making it a robust choice for classifying the iris dataset when configured with the current settings. And then moving on to the next step is the model bidding. So here, leveraging the pre-processed and partitioned iris dataset, multiple supervised learning models are applied using SAS Model Studio. And then hyperparameters such as tree depth, learning rate, and the number of trees are configured and refined using the validation set to prevent overfitting and enhance generalization. As part of the modeling process, performance metrics are recorded for each model and compared as shown below. So as I mentioned earlier, this is an overall comparison table for each algorithm used, which is decision tree, gradient boosting, and also random forest. And then moving on to the next is the model evaluation and interpretation. So here, among the models tested, the decision tree model configured with class-level target interpretation achieves the highest classification accuracy of 0.9583 with a low average square error of 0.0324, demonstrating strong predictive comparability and also interpretability. And then lastly is the model deployment, where as you can see, the complete modeling pipeline includes data import, variable management, imputation, transformation, feature selection, modeling, and also model comparison. So here, the pipeline branches into 4 supervised learning algorithms. Firstly, logic regression is also served as a baseline linear classifier offering a straightforward model for comparison. And then decision tree provides interpretable rule-based decisions that are easily to visualize and understand. And then gradient boosting builds a more powerful model by iteratively improving predictions through an assembly of weak learners. And then lastly, random forest further enhances generalization by constructing multiple decision trees using bootstrap subsets of the data. Finally, the model comparison node aggregates performance metrics from all the 4 models. That, as you can see, the pipeline supports integration for real-life classification and is adaptable for future data imports. Sorry. And then for overall, this structure life cycle ensures consistent accuracy and efficient deployment in practical systems. That's all from me, and I shall pass to my next team member.
All right, thank you, Tamal. The next part will be the result and conclusion. Next slide. Okay, the image here showing the model summary performance. 4 machine learning models will test to see which one best classify the RE's flower species. We compare their accuracy and other key metric like AUC and leaf values. So both the decision tree and random forest model stood out by giving the perfect and consistent result, making them the most reliable for this task. Next slide. Right, so this slide presents the comparison of 4 model tests on the iris dataset, which is the decision tree, forest, logistic regression, and gradient boosting. So among these, the decision tree model emerged as the best performer. It achieved a perfect accuracy of 100% and more importantly, had the lowest average squared error at just 0.004. It did also score a perfect 1 in both the KS statistic and AUC, which indicates the excellent ability to separate the classes. The cumulative leaf values were also strong, especially in the top segments. On the other hand, the forest model performed similarly in terms of the accuracy, KS and AUC, but had a slightly higher error rate of 0.0146, making the decision tree more precise overall. On the other hand, logistic regression and gradient boosting had much lower accuracy at only 66.67% and underperformed in terms of class and separation and lift. So overall, this comparison highlights the tree-based model, especially the decision tree, are well suited for this clean and structured dataset like IRIS. So that's all for me. I will pass to the next presenter.
Thank you so much. Visual interpretation of decision tree model. So model performance comparison thing. So this slide compares all models using 4 key evaluation tools. So as you see, row curve, cumulative lift chart, and fit statistics summary, and F1 score, FC cutoff. So row curve, decision tree, and forest models have curves near to top left, showing excellent classification, logistic regression, performance poorly, and gradient boosting is moderate. So cumulative lift chart, tree based models, decision tree, and forest are strongest at identifying through postly modifies early. logistic regression is weak and gradient boosting is only slightly better. So as you see, fit statistic summary table, decision tree and forest achieve the best AUC, lowest ASE, and highest Gini. Logistic regression is stable but less accurate. Gradient boosting shows inconsistent result. F1 score and VS cutoff. Three basic models maintain high F1 scores across thresholds, providing balanced performance. Logistic regression drops quickly outside 0.5 and creating boosting in unstable. So next slide, please. So as you see, next slide is like a visual interpretation of a decision tree model. So decision tree inputs. This slide highlights the important feature in decision tree. Variable import better width is a top of feature of for splitting consistent with domain knowledge. Score inputs, battle and battle length CM were used as a continuous input to maintain consistency during prediction. So next slide, please. So finally, visual interpretation for a decision tree model. This slide shows the final structure of the decision tree, built using information gained ratio and then branded for simplicity. Final tree has a tree level and 4 leaves with 0 misclassification on validation test sets. So better width remains the most important feature. Overall, tree basic model delivered best result with high accuracy and reliability. Thank you so much.
So thank you to my teammate and good day everyone. So in this part of the presentation, I will walk you through the demonstration or to say a detailed implementation of our machine learning workflow using SAS Model Studio, specifically for the iris flower classification task to do pattern recognition. So our pipeline basically begins with the data node where we import the iris dataset, and this dataset actually contains 150 samples, as you can see here. And each 4 numeric features, which is the sepal length, sepal width, petal length, and petal width, along with one categorical target variable, which is the species of the flower, called Sentosa, versicolor, and virginica. Okay, so in the next pipeline, which is the managed variable, is where once the dataset is imported, the dataset is actually passed to the managed variable mode, and where we assign the roles in terms of the species variable is set to target with a nominal level, and it is categorical. And the 4 measurements are set into inputs and interval level since they are numerical and continuous. The ID variable is marked as rejected, which is because it holds no predictive value and would only add noise to the module. So next is the imputation, where while the iris dataset does not contain missing values, this node is included to ensure our pipeline is compatible with other datasets that might. So it prepares the model to handle missing values automatically in future and in real case scenarios by applying rules like mean or mode imputation depending on the variable type. So as we can see the results, here we can see there are no missing values as the data has been imputed. And yes, there are no number of missing values or anything sort of for all our continuous and numerical data that will be used to determine the continuous nominal data, which is the species. Okay, so we can go back to the pipeline. Okay, so next is the transformations module we have added here. And this is basically after that, we use the transform variables node to normalize our numerical features. This step is actually to ensure that all the features are on similar scale, which is critical for distance-based models and also to improve the convergence during training. For example, the petal length and sepal width might originally be different in ranges, which could actually affect the model accuracy if it's not scaled. So basically, we are normalizing all the data to have a better and predictive model. So next is we also have a variable selection where we use the variable selection node to identify which features are most important for prediction. In our case, it's petal width and petal length, where it is consistently ranked as the top predictors across all models. And this is not only to improve the performance, but it is also to improve the model's efficiency and accuracy. And you see, yes, as the results shows here. So next, we will move on to the model building, where we train 4 different machine learning models in parallel. Firstly is decision tree, and we have logistic regression, random forest, and gradient boosting. So the decision tree is chosen for its interpretability, and as in logistic regression was as a baseline model for comparison, random forest is basically for robust assemble training, and gradient boosting was chosen for capturing complex patterns through a iterative training. So each model is actually trained on a training data set and tuned using the validation set and tested using the testing data set. And hyperparameters like the tree depth, number of trees, and learning rate are optimized for the model's performance as shown here. We have set and tuned the hyperparameters for a better model accuracy and efficiency. So once all these models are actually basically trained, we reach the model comparison part where the model comparison node is added. And this node basically aggregates and the performance of results of all 4 models according to like multiple metrics such as accuracy, average squared error ASE, AUC, which is the area under the curve, and the misclassification rates, including the KS statistics. So based on this analysis, the decision tree and random forest models achieve like a perfect classification results with each 100% accuracy of an AUC of 1, making them the best performing models in this dataset. So let me show you the results that support this interpretation. Yes, so decision tree is basically the champion model, which shows that it has the highest accuracy rate, and these are the properties, the KS statistics, and it is tested using ASE. Basically, this is to show the cumulative lift of all models. This is the lift using all data sets, each model. So this is the ROC chart for all models, the accuracy chart for all models. As you can see, the decision trees charts are on 1 because of the accuracy of the model, and the F1 score is also same. That this shows decision tree actually has a highest accuracy rate, and this is the fit statistics to support the results. Sorry. Yes. So this is basically the pipeline comparison to show that the champion model is actually decision tree, and it has a KS score of 1. And this is the tree diagram based on our hyperparameters tuned. and our confusion matrix to show the probability of that event, and the pruning error plot for misclassification weight, which is low when it is trained, and the variable importance, where petal width, as mentioned before, and petal length is basically the rated as a higher important variable in terms when we are training and validating the data. In the score inputs, as mentioned, the variable targets were petal length and petal width. And this is the leaf reports, cumulative leaf report for decision tree, as it is our champion model. And the ROC. This is the accuracy chart to support our findings, and this is the F1 score to also support our finding, as it is in the score of 1. This is the fit statistics. And this is the event classification, as it has a lower number of incorrect data. And this is the nominal classification for the type of flower, our target variable. Percentage plot. We have count plot as well. So basically, this is the output for our tree split procedure, which is for the decision tree, where we use a pruning method of reduced error, and all the hyperparameters are actually mentioned. And we have also conducted a data partitioning, where we used 70, 15, and 15 percentage, where 105 data is basically used for training, 21 is for validation, and 24 is for testing. And this, and these are the insights from our pipeline for our project. So, as we can see here, the end-to-end implementation in SaaS model ensures a structured and reproducible and scalable pipelines, from data cleaning to transformation to model training and evaluation. So it allows a transparent performance comparison and makes it easier to deploy the most effective model into real-world applications, such as plant identification tools and smart agricultural systems. So that's all for me for today's presentation. So thank you.
So the next part is the conclusion. So basically, tree-based model, especially the decision tree and forest, outperform others with near perfect accuracy, AUC, and consistent performance. Gradient boosting show moderate result but lack stability, while the logistic regression struggle with the non-linear patterns. So overall, tree-based model are the best fit for the structured dataset like IRIS. So that's all from us. Thank you so much.